In this lecture, I'm going to demonstrate switching between access levels. I have created a new project here, access levels. I'm going to my earlier project, that is operation modes, and I will copy the same code, paste it here. And now let me do some modifications here. First of all, the program starts with thread mode plus privileged access level, remember. Before calling this function, let me switch off the privileged access level. That means let's make the thread mode unprivileged. That's why I would write a small function, change access level to unpriv. Let me implement this function right here. Let's understand later how to change the access level. By changing the access level to unprivileged, I'm going to generate an interrupt. What happens here is when you go to the generate interrupt function, since the thread mode is in unprivileged access level, you cannot able to execute these instructions. You cannot change these system specific addresses of the processor. These have restricted access. That's why we should see a processor fault. Let's see that by executing this code on the target. First, let's understand how to change the access level. You know that to change the access level, you have to change something in the control register of the processor. Let's explore that. I am in the generic user guide, and let me search for control register, which is right here, control register. Here, as I explained in the earlier lecture, you have to make this bit as 1 to make thread mode as unprivileged. How do you access this register? So as I explained previously, this is a core register. This is not a memory mapped register. This doesn't come with its own address. You can't use your C pointer manipulation to access this register. You have to use pure assembly instructions. So we'll use inline assembly code. Anyway, you already know how to write the inline assembly instructions in a C program. First, let's read this register. After that, let's modify the value, and after that, let's write back. Let's use read, modify, and write technique. Let's get back to the code. How do you read the special register, which is control register? First, let's use MRS, read. I would use the first general purpose register R0, and after that, I would use control. Let's use our inline assembly syntax, ASM, volatile, and I have to keep this instruction inside the double quotes. We got the value into R0. After that, let's modify it. We have to set the 0th bit. For that, I can use ORR instruction, or this instruction you can again refer from to get the details of ORR instruction. You can go to data processing instructions. Here it is, ORR, logical OR. You can use this to set a bit. Destination, operand 1 and operand 2. That's a syntax. You can explore this document for more information. I would use destination as R0 ORed with. Let's use immediate value 0x01. Because my goal is to set the 0th bit. This is operand 1, operand 2, and the value after ORing will be put into R0. And after that, write back. For write back, you can explore MSR instruction. MSR, special register RN. Let's use MSR instruction. This is a place where we are changing the privileged access to unprivileged access. After that, the function returns. here. And after that, the function enters generate interrupt. Now the code cannot access these addresses because these addresses can only be accessed by being in privileged access level. So now the code is in unprivileged access level. Trying to access those addresses will cause a processor fault exception. We are going to observe that now. That's why let's implement a fault handler. So don't worry about fault handlers. We have a dedicated section explaining faults and faults handler. I would just implement a hard fault handler here. You can observe that control comes to this fault handler, and I would trap the code here in an infinite loop. Let me just build this code. Let me just debug this code. Just observe the control register because we modify the control register. Initially it is 0, you can see here, and now let me just execute this and let's step into this function. Let's observe the value of R0. R0 is 10. Let me execute step into. R0 is 0 because we read the value of control to R0. Step into, yes, R0 becomes 1 and control register modifies here. Let's observe the control register. This is a problem with the IDE. Control register value is actually 1. I'm not sure whether it is a problem with the IDE or the debugger cannot able to access that. So it should show 1 here actually. But let's assume that control register's value is 1. And now let's exit this function. Let's enter into this function. Here you can see that I'm trying to access this address, which only permits privileged access. Now I am in unprivileged access level. Just check what happens here. I'm going to execute this. Here it is. There was a fault. And so the control reached the hard fault handler. Here you can see that. If I just check the fault analyzer here, go to show view and fault analyzer, and you can see that it is actually a hard fault, bus memory management or usage fault. The exact cause of fault is usage fault. And now it is trapped here. Then what's the use case of this? Let's imagine an application which involves embedded kernel or real-time operating system. A RTOS-based project has two components. One is a kernel and another one is user task. So the user task should not affect or should not modify some of the system level settings of the processor. The user task should not trigger any interrupt or it should not turn off any interrupts. If that happens, then the whole system fails, isn't it? That's why before running a user task, the kernel can change the access level to unprivileged, and then it can launch the user task. That's why the real-time operating system or secured systems always launch user task in unprivileged access level. And if the unprivileged code wants any services, then it can trigger system call, and that system call will be serviced by the kernel code. That's a procedure or that's a design which is followed in a secure and robust system. And ARM Cortex-MX processor gives that features in the processor itself. By using those features, you can build secure and robust embedded software solutions. That's about switching from privileged access level to the unprivileged access level. The question is, how do you switch back from unprivileged access to the privileged access? How do you do that? Let's discuss that. Let's understand that with this diagram. First, processor started with thread mode and with a privileged access level. Control register was 0. And after that, you made control register 1. That means you moved to unprivileged access level. Once you are in unprivileged access level, you cannot go back to the privileged access level. That's not possible. Why? Because for the simple reason, by being in unprivileged access level, you cannot access this control register. That's a trap, because to modify control register, you need privileged access level. That is one way you can go back to the privileged access level. That is to move the mode of the processor from thread to the handler mode. How do you do this? By triggering an system exception or by triggering an interrupt. Once interrupt hits the processor changes the mode to handler mode, isn't it? The ISR runs. As I said in the previous video, ISR always executes with privileged access level. Here you can modify the control register. Modify the control register back to 0 and then exit to thread mode. The thread mode will be privileged access level. Once you changed thread mode's access level from privileged to unprivileged, so to change back to privileged, you have to take this path. That's the only path available. That is, you have to trigger a system exception or interrupt, go to the handler mode and modify the control register there, and then come back to the thread mode. I hope you get the idea about switching between privileged access level and unprivileged access level. And that's it for this video, and I'll see you in the next lecture.